The more images we get of 3I-ATLAS, the more alien and unnatural it looks. In the latest development, the November 5th image from Lowell Observatory just documented something that has comet scientists in emergency sessions. 3I-ATLAS has turned green again. It was green, then shifted to blue, and now it's back to green. A colour-changing sequence that has no precedent in cometary observations. The green glow comes from diatomic carbon fluorescence, which demands massive dust production to generate that much emission. But there's no tail, no debris field. The object is accelerating like it's shedding material, yet nothing is there. Comets don't change colours. They don't glow this intensely without producing visible tails. Scientists are now running calculations to determine whether natural physics can produce what November 5th captured, or whether we've just documented an object that shouldn't exist. This investigation matters, because the answer determines whether we're tracking a comet with impossible behaviour, or something far stranger that's just passing through. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Green Enigma. On November 5th, 2025, astronomers at the Lowell Observatory pointed their Discovery telescope toward a patch of sky where something impossible was happening. They captured an image of interstellar object 3I-ATLAS, and what they saw shouldn't exist according to everything we know about comets. The object glowed an intense emerald green against the blackness of space, burning with a brilliance that suggested massive chemical activity. But here's what made seasoned astronomers pause mid-coffee. There was no tail. None. Just a clean, compact sphere of light hovering in the frame like a cosmic stoplight frozen in space. You need to understand what makes this so unsettling. When a comet swings close to the Sun, it should behave in predictable ways. The heat wakes up the ices trapped inside, turning them directly from solid to gas in a process called sublimation. This outgassing creates pressure that pushes material away from the nucleus, forming the classic comet anatomy we've seen in textbooks since childhood. A glowing head called the coma, and behind it, a tail of dust and gas that can stretch for millions of miles. The tail always points away from the Sun because radiation pressure from sunlight literally blows it backward, like cosmic wind against a sail. 3I-ATLAS had just passed perihelion, its closest approach to our star, on January 13th, 2025. It should have been at peak activity, shedding material like a dog shaking off water. The tail should have been obvious, brilliant, unmistakable. Instead, astronomers saw what looked like a perfectly formed green pearl. The object sat at approximately 1.38 astronomical units from the Sun and roughly 2.23 astronomical units from Earth. For context, 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles. At that range, with the energy it had absorbed during perihelion, 3I-ATLAS should have been displaying a spectacular dust tail arcing across the sky. Telescopes should have captured streams of particles catching sunlight, creating that iconic comet glow that has inspired humanity for millennia. What they got instead was this impossibly clean light source that refused to conform. The green colour itself tells us something important. When sunlight hits cometary material, particularly organic compounds and ice mixtures, it breaks apart larger molecules through a process called photolysis. Among the fragments produced are pairs of carbon atoms bonded together, which scientists call diatomic carbon, or C2. These molecular duos absorb ultraviolet light from the Sun and then re-emit it at specific wavelengths in the green part of the spectrum. It's the same reason some Earth comets glow green when they visit our neighbourhood. The chemistry is well understood, almost routine. We see C2 emission, we know organic rich material is, being processed by solar radiation. Simple. Except nothing about 3I-ATLAS is simple. The green glow confirms that yes, something is happening on or near the surface of this object. Chemical reactions are taking place. Material is being energized and broken down. The signature is unambiguous. But if enough material is breaking apart to produce that intense green color, where is the debris? Where is the dust that should accompany those carbon molecules into space? You don't get one without the other in normal cometary physics. It would be like seeing smoke without fire, or watching someone's hair blow wildly in wind that doesn't exist. The signature and the structure should match, but they don't. This is where the paradox deepens into something genuinely strange. 3I-ATLAS exhibits what astronomers call non-gravitational acceleration. Its trajectory through the solar system doesn't quite match what gravity alone would predict. There's an extra push, a deviation from the expected orbital path that suggests something is creating thrust. For comets, this makes perfect sense. As gas jets erupt from the surface, they act like tiny rocket engines, nudging the object slightly off course. We've measured this effect on dozens of comets. It's expected, it's normal, but here's the knife's edge. That acceleration requires mass loss. You can't push without something to push with. Momentum has to go somewhere. If 3I-ATLAS is accelerating due to outgassing, it must be ejecting material at a significant rate. Scientists have run the numbers. Based on observations of the inner coma, the fuzzy region immediately around the nucleus. They estimate the object is losing somewhere between 6 and 60 kilograms of mass every second. For perspective, that's roughly the weight of a full-grown human being launched into space every second at the low end, or 10 people at the high end. Hour after hour, day after day, the object sheds its substance into the void. That much mass loss should create an absolutely obvious trail of dust and gas. It should produce a tail you could photograph with amateur equipment from your backyard. Yet the November 5th image shows nothing, or at least nothing conventional instruments can detect clearly. The Hubble Space Telescope had captured 3I-ATLAS months earlier, on July 21, 2025, and that image showed something peculiar, a teardrop-shaped dust cocoon surrounding the nucleus. The morphology suggested material was present, but distributed in ways that didn't quite match expectations. Some astronomers wondered if this was an early warning sign of the weirdness to come. Perhaps the object was already behaving strangely before perihelion, and we simply didn't have the context to recognize it yet. Now post-perihelion, when the tail should be most prominent, it appears to have vanished or transformed into something our instruments can barely perceive. You might think this is a problem of distance or viewing angle, and we'll get to that. But let's sit with the discomfort for a moment. We have an object that glows green, confirming active chemistry. We have measured acceleration, confirming mass loss. We have estimates suggesting significant outgassing rates. And we have an image that shows none of the expected consequences. It's as if the object is following half the rulebook while completely ignoring the other half. Astronomers who have spent careers studying comets find themselves in the uncomfortable position of saying this should not look like this, while simultaneously confirming that yes, the observations are real. For a general audience already familiar with comets from news coverage of spectacular visitors like Hale-Bopp or Neowise, this gets under the skin. You know what a comet should look like. We all have that mental image. Fuzzy head, sweeping tail, a cosmic exclamation point drawn across the sky. 3I-ATLAS refuses to cooperate with that image. It presents as something cleaner, more controlled, more contained than the chaotic ice and dust bodies we're used to. The object appears too neat, too organised, as if someone had taken a normal comet and edited out all the messy parts. What happens next in our investigation becomes crucial. We need to peel back layers of explanation, starting with geometry and moving through chemistry, physics, and ultimately into the realm of speculation that makes scientists uncomfortable. Could the tail simply be hidden by our viewing angle? Are we looking at this thing from a perspective that conceals its most obvious feature? Or is the tail genuinely missing, which would imply something far stranger about 3I-ATLAS's composition or behaviour? Maybe we're not looking at a comet at all, but something that merely resembles one in certain specific ways while breaking fundamental rules in others. The more data we collect, the more uncomfortable the situation becomes. Each new observation should clarify the mystery, narrowing down the possibilities until we arrive at a satisfying natural explanation. Instead, each image seems to expand the puzzle. The November 5th photo doesn't answer questions, it raises new ones. Why green but not dusty? Why accelerating but not trailing? Why does this object insist on behaving like a comet in some ways, while stubbornly refusing to complete the picture? We're going to spend the next 14 parts examining this mystery from every angle we can think of. We'll look at the physics that might explain the acceleration without the tail. We'll explore geometry and viewing angles that could hide what we're looking for. We'll dive into exotic chemistry and plasma interactions. We'll compare 3I-ATLAS to previous interstellar visitors and ask whether we're seeing a pattern or an anomaly. And yes, we'll eventually confront the possibility that makes headlines, but gives scientists heartburn. What if this isn't entirely natural? But let's not get ahead of ourselves. Right now, we're standing at the beginning of an investigation, staring at a green light in space that refuses to make sense. The better we look at 3I-ATLAS, the more questions it raises. The clearer our images become, the less clear our understanding grows. Something about this object violates our expectations in ways that feel almost deliberate, almost crafted, almost like the universe is testing whether we're paying attention. So the question isn't just what is 3I-ATLAS? The question is, what happens when an object from another star system arrives in our neighbourhood and proceeds to break every rule we thought we understood? What does it mean when the cosmos sends us something that looks almost right but not quite? Something that fits the category of comet just well enough to be classified, but badly enough to keep astronomers awake at night? Welcome to the mystery. Let's see how far down this goes. Part 2. When physics misbehaves. When an object moves through space, gravity writes its story. The sun pulls, planets tug, and the resulting trajectory becomes a mathematical certainty that we can predict centuries in advance. This is orbital mechanics, the clockwork precision that lets us send spacecraft to distant worlds using calculations made years before launch. It works because gravity is consistent, measurable, and obeys rules that haven't changed since Newton first scratched them onto paper. 3I-ATLAS follows these rules mostly, but there's a problem, a deviation, a whisper of something else influencing its path. Scientists noticed it early in the observation campaign. The object's trajectory didn't quite match the predictions based solely on gravitational forces. There was extra acceleration, a slight but measurable push that couldn't be explained by the sun's pull or the gravitational influence of planets. This is what astronomers call non-gravitational acceleration, and for comets, it's not unusual. In fact, it's expected. When ice on a comet's surface heats up and transforms directly into gas, that gas explodes outward with enough force to nudge the entire object. These outgassing events act like tiny rocket engines scattered across the surface, firing randomly as different patches of ice catch sunlight. The cumulative effect produces measurable changes in the orbit. We've seen this countless times with solar system comets. Halley's Comet, which visits us every 76 years or so, experiences non-gravitational acceleration every time it swings past the sun. Scientists account for it in their predictions. They measure the outgassing rates, estimate the force produced, and adjust the orbital calculations accordingly. It's routine, it's understood. It's one of those cosmic behaviours we've successfully explained and incorporated into our models. So, when 3I-ATLAS showed non-gravitational acceleration, astronomers nodded and said, yes, of course it's a comet. But then they looked for the tail, and that's when the routine explanation started falling apart. Let me walk you through why this matters. When a comet loses mass through outgassing, that material doesn't just disappear, it goes somewhere. Gas molecules and dust grains get blown away from the nucleus by solar radiation and the pressure of escaping volatiles. This debris forms the coma, the fuzzy cloud immediately surrounding the solid nucleus, and eventually the tail that stretches behind the comet like a banner. The amount of material in the tail directly correlates to the rate of mass loss. If you're shedding a lot of material, you produce a big, obvious tail. If you're shedding less, the tail is fainter, but still visible. The physics here is straightforward. Matter in equals matter out, and we can measure both. 3I-ATLAS's non-gravitational acceleration implies it's losing mass at rates estimated between 6 and 60 kilograms per second based on observations of the inner coma. Let's put that in perspective. 6 kilograms per second means the object is ejecting roughly 130,000 pounds of material every day at the low estimate. 60 kilograms per second would be more than £1 million per day. These aren't trivial amounts. This is substantial mass loss that should create equally substantial visible evidence. But the November 5th image shows minimal evidence of a tail, if any at all. The object appears compact, contained, almost pristine. This creates a physics problem that makes scientists uncomfortable. You can't have significant outgassing without debris. You can't generate enough force to alter an orbit without throwing material into space. And you can't throw material into space without creating a visible structure, especially when we're talking about rates this high over periods of weeks or months. The math doesn't work. The observations don't match. Something is wrong with either our measurements or our understanding. This is where comparisons to previous interstellar visitors become illuminating. 1I/Oumuamua, discovered in October 2017, was the first confirmed interstellar object ever detected passing through our solar system. It was bizarre in almost every way. Elongated, tumbling, no visible coma or tail despite showing non-gravitational acceleration. Scientists struggled to explain it. Some proposed exotic outgassing of hydrogen, which would be invisible to optical telescopes. Others suggested it might be a fragment of a larger body, with unusual composition. A few, including Harvard astronomer Avi Loeb, proposed it could be an artificial light sail, a thin reflective structure using sunlight for propulsion. 2I/Borisov, discovered in August 2019, seemed more conventional. It displayed obvious cometary activity with a clear coma and tail. Spectroscopic observations confirmed water vapour and cyanide, typical cometary compounds. It's behaved mostly like comets from our own solar system, just arriving from a different star. Astronomers breathed a sigh of relief. Apparently interstellar comets could be normal after all. Oumuamua was perhaps just an outlier, a statistical fluke. 3I-ATLAS seems determined to split the difference. It shows activity like Borisov, confirming it's not an inert rock. It displays the green glow of C2 emission, textbook cometary behaviour. But its tail situation echoes the mystery of Oumuamua, present but anomalous, visible but not in the ways or amounts expected. The object combines weird traits from both predecessors, while adding new puzzles of its own. It's as if the cosmos is gradually showing us a spectrum of possibilities, each interstellar visitor teaching us that our categories might be too narrow. The modelling issues become apparent when scientists try to reconcile the observed acceleration with the minimal tail. Standard cometary models assume most outgassing produces both gas and dust. The ratio varies, some comets are gas-rich, others dust-rich, but there's always both components. The dust is crucial because it's what we see most easily. Gas molecules are often transparent or emit at wavelengths our optical telescopes can't detect well. Dust scatters sunlight, making it visible. A healthy dust component means a bright, obvious tail. 3I-ATLAS seems to be outgassing without proportional dust production, which violates the typical comet composition models. Could this be exotic outgassing? Perhaps. Some comets contain super-volatile ices, materials like carbon monoxide or carbon dioxide that vaporize at lower temperatures than water ice. These molecules are lighter and faster, producing more thrust per unit mass. If 3I-ATLAS is rich in supervolatiles and poor in dust, it might generate the observed acceleration while producing a faint gas-dominated tail that's hard to see. This is plausible. It fits within natural explanations. But it requires the object to have a very unusual composition, different from any comet we've studied up close in our own solar system. There's another possibility that scientists discuss quietly in conferences, but rarely put in papers. Could there be something even more exotic happening? Molecular hydrogen outgassing, for instance, would be completely invisible to optical telescopes. Hydrogen is the most abundant element in the universe, and some models suggest icy bodies could trap it in clathrate structures, cage-like arrangements of water molecules that hold gas. If 3I-ATLAS is outgassing primarily hydrogen, it could produce acceleration without visible debris. This explanation has been proposed for Oumuamua and might apply here, but it's speculative, requiring conditions and compositions we've never directly observed. And then there's the explanation that makes press releases, but causes astronomers to wince: engineered propulsion. If the acceleration isn't from outgassing at all but from something artificial, a controlled vent or propulsion system, then the missing tail makes perfect sense. You wouldn't expect debris from a spacecraft's thruster. This hypothesis leaps far beyond conventional science into the realm of speculation. But given the oddities accumulating around 3I-ATLAS, some researchers argue it deserves consideration, if only to rule it out systematically. Most astronomers remain cautious. Natural explanations still dominate the discussion. The scientific community has learned hard lessons about jumping to extraordinary conclusions without extraordinary evidence. Every mysterious object in astronomy history that seemed artificial turned out to be natural once we understood it better. Pulsars were briefly called LGM signals, standing for little green men, before we realised they were rapidly spinning neutron stars. Tabby's star dimmed mysteriously, prompting alien megastructure speculation, before dust and debris offered more mundane explanations. The pattern is clear. Weird doesn't mean alien. It usually just means we need better data or better models. But admit there's something compelling about 3I-ATLAS's refusal to cooperate. The object seems almost designed to frustrate our expectations, checking boxes for comet, while leaving others conspicuously blank. It's active but clean. It accelerates but doesn't trail. It glows green from chemical reactions but hides the physical products of those reactions. Every explanation requires adding caveats, special conditions, unusual circumstances that push the boundaries of what we consider typical. The Hubble data provides crucial constraints. Observations suggest the nucleus has a radius no larger than 2.8 kilometers, assuming an albedo, or reflectivity, of 0.04, which is typical for dark cometary surfaces. That's a small object, roughly 5.5 miles across at most. Small bodies have less gravitational self-attraction, meaning they can lose material more easily, but also making the mass loss to acceleration ratio more dramatic. Every kilogram of material ejected has a bigger proportional effect on velocity. This sensitivity means the physics of outgassing should be even more obvious, even more visible, not less. So, where does this leave us? We have confirmed that 3I-ATLAS is accelerating beyond what gravity predicts. We have estimates of its mass loss rate that seem inconsistent with the observed tail, or lack thereof. We have models that struggle to reconcile these facts using standard cometary physics. We have an object that insists on being complicated in ways that defy our expectations, while still showing just enough conventional behaviour to be classified as a comet. Physics, it seems, is misbehaving. Or perhaps more accurately, 3I-ATLAS is behaving according to physics we don't fully understand yet. Maybe it's revealing gaps in our knowledge about cometary composition, about how interstellar space weathering might alter surface properties, about interactions between solar radiation and exotic materials. Or maybe it's showing us something we've never seen before, something that doesn't fit neatly into categories we invented based on solar system objects alone. The next piece of this puzzle involves examining the geometry of our observations. Maybe the tail isn't missing at all. Maybe we're just looking at this thing from exactly the wrong angle, and what appears to be an absence is actually a trick of perspective. That would be convenient, wouldn't it? A simple explanation that preserves our understanding while explaining the anomaly. Let's see if geometry can save us from the growing suspicion that 3I-ATLAS might be genuinely profoundly strange. Part 3. The disappearing tail. Imagine trying to photograph a train from directly in front of it on the tracks. You'd see the locomotive's face, the headlight, maybe a hint of the cars behind, but the length of the train would be compressed into near invisibility by perspective. You wouldn't conclude the train has no cars. You'd recognise that your viewing angle makes them difficult to perceive. Now apply this logic to a comet tail, which is essentially a train of dust and gas particles stretched along the comet's orbit, and you begin to see why astronomers aren't necessarily panicking about 3I-ATLAS's missing tail. Maybe it's not missing. Maybe it's just hidden by geometry. The traditional image of a comet shows the tail streaming behind like hair blown in wind, clearly separated from the head. But this only happens when we observe the comet from a favourable angle, typically when the comet is well away from the Sun as seen from Earth. The tail always points away from the Sun due to radiation pressure and solar wind, so if we observe a comet when it's between us and the Sun, or when the Sun-Comet-Earth angle is small, the tail points directly toward or away from us. In such cases, the tail appears foreshortened, compressed, potentially invisible even if it's actually quite substantial. This is Geometry 101 for comet observers, a well-understood effect that has fooled astronomers before. 3I-ATLAS on November 5, 2025 sat at approximately 1.38 astronomical units from the Sun and about 2.23 astronomical units from Earth. The solar elongation, the angle between the Sun and the object as seen from Earth, was small, somewhere around 10 to 13 degrees. This is an unfortunate geometry for tail detection. We're essentially looking at 3I-ATLAS with the Sun almost directly behind us, meaning any tail pointing away from the Sun would be pointing nearly toward Earth. The foreshortening effect could be severe. What might appear as a long, sweeping structure from a different angle could compress into a small, faint glow surrounding the nucleus when viewed, head-on. This explanation should comfort us. It suggests nothing weird is happening. We're just suffering from bad luck in viewing angle. As 3I-ATLAS continues its journey away from the Sun, and Earth's position changes relative to both, the geometry will improve. The angle will open up. The tail, if it exists, will gradually become visible as it separates from the nucleus in our field of view. We just need patience and time. This is the conventional wisdom, the safe bet, the explanation that requires no new physics or exotic hypotheses. Many astronomers publicly favour this view, and with good reason. But there's a problem with the geometry explanation that makes it less satisfying than it first appears. The foreshortening effect, while real, shouldn't make a bright comet tail completely invisible. It might make it harder to see, sure, compressing it into a smaller angular area. But if 3I-ATLAS is truly losing 6 to 60 kilograms per second, and if that material is forming a normal dust tail, we should still detect brightness enhancements, radial structures, or at least some evidence of material extending from the nucleus even in a compressed view. The November 5th image shows a remarkably clean symmetric source. There are no obvious radial streaks, no elongations, no hints of tail structure even allowing for foreshortening. It looks, for lack of a better word, too perfect. The Hubble Space Telescope's July 21st observation, captured months before perihelion, adds another layer to this puzzle. That image showed 3I-ATLAS with a teardrop-shaped dust cocoon, an asymmetric structure suggesting material was already being processed and distributed around the nucleus. This wasn't a classic tail, but it wasn't perfectly symmetric either. The morphology hinted at complexity, at dust dynamics that didn't quite follow textbook predictions. Some astronomers interpreted this as an early warning sign, a suggestion that 3I-ATLAS's dust behaviour might be unusual from the start. There's also the phenomenon of anti-tails to consider. Occasionally, comets display what appears to be a tail pointing toward the Sun, violating the basic rule that tails point away. These aren't actual reverse tails, but projection effects caused by large dust particles that lag behind the comet in its orbit. When viewed from certain angles, these lagging particles can appear sunward of the nucleus, creating the illusion of an anti-tail. Hubble's earlier imagery might have captured such effects, suggesting the dust distribution around 3I-ATLAS is complex and three-dimensional, not simply a straightforward tail streaming behind. But here's where geometry becomes less of a saviour and more of a complication. If the dust around 3I-ATLAS is distributed in unusual ways, forming cocoons or shells or asymmetric structures rather than classic tails, that's actually evidence of unusual behaviour, not explanation of normal behaviour seen from a bad angle. Normal comets produce predictable dust distributions. The particles get blown back by sunlight, creating a tail that follows well-understood physics. If 3I-ATLAS's dust is doing something different, forming structures that don't match predictions, then the geometry explanation just moves the mystery rather than solving it. We'd still need to explain why the dust behaviour is atypical. Several hypotheses attempt to explain a weak or unusual tail beyond simple viewing angle effects. One possibility involves very fine dust grains, smaller than typical cometary dust. Tiny particles get accelerated more efficiently by radiation pressure because they have more surface area relative to their mass. They'd be swept away from the comet rapidly, dispersing into space faster than larger grains. This could create a tail that's diffuse and faint, difficult to detect even under good viewing conditions. But this hypothesis requires explaining why 3I-ATLAS would produce primarily fine dust, when most comets eject a range of particle sizes. Another idea focuses on gas-rich outgassing with minimal dust. If the object is dominated by volatile ices that sublimate cleanly, without dragging much solid material along, the tail would be mostly gas. Gas tails are often fainter in visible light than dust tails, because gas molecules scatter sunlight less efficiently than solid particles. A gas-dominated tail might explain the missing dust, while still accounting for the observed mass loss and acceleration. But again, this requires 3I-ATLAS to have an unusual composition, lacking the refractory dust grains that typically make up a significant fraction of cometary nuclei. There's a more exotic possibility involving the object's history. 3I-ATLAS has been travelling through interstellar space for potentially millions or billions of years before entering our solar system. During that journey, it was exposed to cosmic rays, interstellar radiation, and possibly interactions with interstellar dust or gas clouds. Some researchers speculate that prolonged exposure could erode or alter the surface layers of an interstellar object, removing dust or creating a hardened crust that sublimates differently than fresh cometary material. If 3I-ATLAS's surface was pre-processed by its long journey, its outgassing behaviour might naturally differ from solar system comets that have been protected within the Sun's sphere of influence. Then there's the idea of electromagnetic effects on dust particles. Dust grains in a comet's coma can become electrically charged through interaction with solar ultraviolet light and the solar wind. Charged particles respond to electromagnetic forces, not just radiation pressure. If the solar wind near 3I-ATLAS's orbit creates unusual electric or magnetic field conditions, charged dust grains might be deflected in unexpected ways. Instead of forming a classic tail, the dust could be scattered, dispersed, or even pushed in directions we wouldn't predict from pure radiation pressure alone. This is speculative, but not outside the realm of known physics. We just don't usually need to invoke it for typical comets. What makes the geometry explanation both appealing and frustrating is that it's testable on a human timescale. As weeks and months pass, 3I-ATLAS continues moving away from the Sun. The viewing geometry from Earth will gradually improve, the solar elongation will increase, the angle will open up, and if there's a tail hidden by foreshortening, it will reveal itself. Scientists know this. They're watching. Every new observation is checked for signs of tail emergence. If a conventional dust tail appears as geometry improves, the mystery resolves, the unusual observations get explained away, and 3I-ATLAS joins the catalogue of interesting but ultimately normal comets. But what if the tail doesn't appear? What if geometry improves and we still see a clean, compact object with minimal tail structure? That would be deeply problematic. It would mean the missing tail isn't an artifact of viewing angle, but a genuine absence requiring explanation through either exotic composition, unusual physics, or something we haven't considered yet. It would move 3I-ATLAS from weird but probably natural into territory that demands serious attention and potentially challenges our understanding of what interstellar objects can be. Avi Loeb, the Harvard astronomer who has become associated with controversial hypotheses about interstellar visitors, pointed out that if 3I-ATLAS is outgassing naturally at rates consistent with its observed acceleration, it should have ejected roughly 13% of its nuclear mass as trailing dust by the time it became visible post-perihelion. 13%. That's not a small fraction. That's a significant portion of the object's substance, and it should be visible as a tail even accounting for geometry and viewing conditions. The fact that it's not clearly visible, Loeb argues, suggests either the outgassing is atypical or the object isn't a conventional comet. Many astronomers push back on this reasoning, noting that dust-to-gas ratios vary widely among comets, and without detailed spectroscopy and high-resolution imaging, we can't definitively say what's missing versus what's merely hidden. This caution is scientifically appropriate. Extraordinary claims require extraordinary evidence, and the absence of a visible tail, while interesting, isn't yet extraordinary enough to overturn conventional explanations. Give the geometry time to improve, give the observation campaigns time to accumulate data, and most likely a mundane explanation will emerge. Yet there's something unsettling about how consistently 3I-ATLAS defies expectations in ways that are just subtle enough to be arguable. The tail isn't completely absent. There are hints of faint structures in some images, but it's weaker than predicted, smaller than expected, harder to see than models suggest. The object sits right on the boundary between unusual but natural, and unusual enough to question assumptions. It's as if someone designed this thing to be maximally confusing, to give us just enough conventional behaviour to classify it while withholding just enough evidence to make us doubt that classification. In the coming weeks and months, as 3I-ATLAS moves through space and our viewing angle improves, we'll learn whether the tail was always there, just hidden, or whether it's genuinely anomalous. This is happening in real time. The observation campaigns are ongoing. Telescopes around the world and in orbit are tracking this object, accumulating data that will eventually settle the question. For now, we're in a state of uncertainty, watching a cosmic mystery unfold with no guaranteed resolution. The geometry trap is that it offers us comfort while leaving deeper questions unanswered. Yes, viewing angle matters. Yes, foreshortening is real. But using geometry to explain everything about 3I-ATLAS's appearance requires assuming the object is fundamentally normal, just poorly viewed. And that assumption might be where we're going wrong. Maybe 3I-ATLAS is showing us that interstellar objects don't play by the same rules as solar system comets. Maybe the missing tail is real, and the geometry explanation is the trap, the comfortable lie we tell ourselves to avoid confronting something genuinely strange, arriving from another star. Either way, the tail situation remains one of the central mysteries of 3I-ATLAS. Hidden or missing, the result is the same. We can't fully explain what we're seeing using conventional models, and that uncertainty is what keeps this object in the spotlight, what keeps astronomers watching, what keeps the possibility alive that we might be observing something unprecedented in the annals of solar system science. The question isn't just whether the tail will appear, the question is what it means if it doesn't. Part 4. Green but not alive. The green glow haunts every image of 3I-ATLAS like a signal trying to tell us something we're not quite hearing. That emerald luminescence, captured so vividly in the November 5th observation, isn't mysterious in its mechanism. We understand what causes it. Sunlight strikes molecules of diatomic carbon, 2 carbon atoms bonded together, floating in the coma around the comet's nucleus. These C2 molecules absorb ultraviolet photons, jump to excited energy states and then crash back down, releasing the absorbed energy as visible green light. It's fluorescence, the same basic principle that makes certain minerals glow under black lights, or gives fireflies their luminance. The green tells us unambiguously that carbon chemistry is happening, that organic materials are being broken down and re-emitted as simpler compounds. In cometary science, this is textbook stuff. Imagine sunlight as a hammer striking a complex molecular structure, something like methane ice or frozen hydrocarbons locked in the comet's nucleus. The hammer blow shatters the larger structure, breaking chemical bonds and freeing simpler fragments. Among these fragments are pairs of carbon atoms that happen to stick together temporarily before dispersing further. These C2 pairs are reactive and short-lived, but while they exist, they dance in the sunlight, absorbing and emitting photons in a rhythm that produces that characteristic green glow. It's beautiful, it's chemistry in action. It's also completely expected for an active comet near the Sun. So why does 3I-ATLAS's green glow feel significant? Because while the colour confirms chemical activity, the intensity and pattern of the emission don't quite match what we see in typical solar system comets. The brightness of the green relative to other wavelengths, the distribution of the C2 emission across the coma, the apparent strength of the signal despite minimal dust detection, all of these suggest something unusual about either the composition of 3I-ATLAS or the way it's processing solar energy. The green is there, which is normal, but its specifics are off, which is not. Typical comets show a balance between multiple emission features. You get green from C2, yes, but you also see cyan from neutral carbon atoms, red or yellow from sodium, blue from ionized molecules, and importantly, reflected sunlight from dust grains creating a whitish glow. The overall colour of a comet's coma is usually a blend, a pastel mixture that includes but isn't dominated by any single wavelength. 3I-ATLAS appears intensely, almost purely green in certain images, suggesting either an unusual abundance of C2 relative to other species, or a dust deficit that allows the green emission to dominate visually. This raises questions about the object's ice budget. All comets aren't created equal. They form in different regions of protoplanetary disks, under different temperature and pressure conditions with different mixtures of ice and rock. Some are water-rich, others have significant amounts of carbon monoxide or methane. The ratio of volatile species determines how a comet behaves when heated. 3I-ATLAS formed around another star, in a planetary system potentially very different from our own. Its composition might reflect chemical conditions we've never studied up close. Maybe it's rich in carbon compounds in ways solar system comets aren't. Maybe its formation environment led to an unusual ice chemistry that favours C2 production. There's another intriguing possibility involving the object's surface. 3I-ATLAS has been travelling through interstellar space for an immense amount of time, potentially millions of years, exposed to cosmic rays and interstellar radiation, at levels far exceeding what objects in our solar system typically experience. This radiation bombardment can chemically alter surface materials, breaking down complex molecules, creating radicals and ions, essentially weathering the ice in ways that don't happen to protected solar system objects. Some scientists speculate this pre-processing might create a thin outer layer enriched in certain compounds while depleting others. If 3I-ATLAS's surface was irradiated during its long journey, it might outgas differently than a fresh comet. The radiation could have created a crust enriched in carbon compounds, while depleting lighter volatiles like water. When this material heats up near the Sun, it might produce intense C2 re-tri-M continu emission, because that's what's concentrated in the altered surface layer, rather than reflecting the bulk composition of the nucleus. You'd get a green glow from a thin active veneer, while the interior remains mostly untapped. This would also help explain the minimal dust. If outgassing is restricted to a processed surface layer rather than deep excavation of pristine material, dust production might be suppressed. The concept of a hollowed or pre-eroded comet comes into play here. Interstellar space isn't a perfect vacuum. There are trace amounts of gas and dust, thin beyond imagination, but present nonetheless over cosmic distances. If 3I-ATLAS passed through denser regions of the interstellar medium during its journey, collisions with particles at relative velocities of kilometers per second could have sandblasted the surface, removing loose material and leaving behind a more compact resistant structure. This erosion might have stripped away the fluffy outer layers that typically produce copious dust when heated, leaving only harder, more volatile-rich material that sublimates cleanly. Think of it like the difference between burning a fresh log and burning charcoal. The log produces smoke, flames, and lots of particulate debris. Charcoal burns cleaner, hotter, with less visible waste. If 3I-ATLAS is more like cosmic charcoal than a fresh, icy log, its combustion near the Sun would naturally look different. You'd get intense chemical emission from concentrated volatiles without the dusty mess of a normal comet. The green glow would be bright because the chemistry is efficient, happening in a thin layer optimized for C2 production, rather than distributed through a dirty, heterogeneous nucleus. But this explanation, while clever, requires assuming a very specific history and composition for 3I-ATLAS. We're stacking hypotheses: unusual formation environment, plus prolonged interstellar exposure, plus selective erosion, all combining to produce exactly the weird behavior we observe. Each individual assumption is plausible, but the combination starts feeling contrived, like we're inventing a custom backstory to fit the evidence, rather than discovering it from first principles. There's also the troubling detail that even dust-poor comets typically show some dust. The cleanest, most gas-dominated comets in our solar system still produce detectable dust tails, just fainter ones. For 3I-ATLAS to be essentially dust-free while outgassing at significant rates would make it an extreme outlier, sitting at the far edge of what we consider possible for natural cometary composition. Not impossible, but statistically unlikely enough that it should give us pause. The ratio of C2 to other emission species becomes crucial here. If we had detailed spectroscopy measuring not just the green but the full emission spectrum, sodium lines, carbon monoxide bands, water vapor signatures, ionized species, we could constrain the composition much better. Unfortunately, getting high-quality spectra of a relatively faint, fast-moving object at large distances is challenging. The data exists but isn't yet comprehensive enough to definitively answer whether 3I-ATLAS's chemistry is merely unusual or genuinely anomalous. We're working with incomplete information, trying to solve a puzzle with half the pieces missing. What we can say is that the green glow, paradoxically, both confirms and challenges the comet hypothesis. It confirms because C2 emission is quintessentially cometary, something we see in dozens of active comets and never in asteroids or other non-volatile objects. The green screams comet in a chemical language we understand. But it challenges because the intensity, distribution and lack of accompanying dust don't fit the standard model. It's like hearing someone speak fluent English, but with an accent so strange you can't place their origin. The language is right, but something about the delivery is profoundly foreign. Some researchers wonder if we're seeing selective outgassing from specific surface regions rather than global activity. Perhaps 3I-ATLAS has active patches rich in carbon compounds, while other areas remain dormant. This could produce intense C2 emission from localized jets without widespread dust production. But this just moves the mystery. Why would an interstellar comet have such heterogeneous surface composition? What mechanism would create active carbon-rich patches alongside inactive or dust-free regions? You end up needing to explain the heterogeneity, which is arguably as hard as explaining the original observations. Then there's the possibility that outgassing is happening, but involves materials we're not detecting easily. Carbon monoxide, for instance, outgasses at lower temperatures than water ice. and produces minimal visible signature. If 3I-ATLAS is rich in carbon monoxide or carbon dioxide, it could be losing significant mass while producing faint tails dominated by gas rather than dust. The green C2 might be a minor byproduct, visible and striking but representing only a small fraction of the actual outgassing. We might be seeing the tip of the iceberg, the visually obvious part, while the bulk of the activity happens in wavelengths or materials instruments aren't optimally tuned to detect. Hydrogen outgassing returns as a possibility here too. Pure molecular hydrogen would be completely invisible to optical telescopes, producing no dust and no coloured emission. If the C2 we see is produced from trace contaminants, while the bulk outgassing is hydrogen, we'd observe exactly what we're seeing. Strong green colour from active chemistry, but minimal tail from the invisible hydrogen escaping into space. This would elegantly explain both the acceleration and the missing dust, but it requires 3I-ATLAS to be trapping and releasing hydrogen, which is exotic in cometary science, though not physically impossible. The cultural and psychological dimension of the green glow deserves mention. Green has associations in human perception, alien technology in science fiction films, radioactive materials, unnatural processes. When the public sees that vivid emerald colour in the November 5th image, there's an instinctive sense of something is off that transcends the scientific details. It looks too bright, too pure, too intentional. Scientists know this is just fluorescence, mundane chemistry, but the visual impact still works on us subconsciously. The green makes 3I-ATLAS memorable, disturbing, harder to dismiss as just another comet passing through. Whether the object's chemistry is exotic or merely unusual won't be settled until we get better data. Future observations with higher spectral resolution, infrared measurements to detect molecules invisible in optical wavelengths, and multi-wavelength campaigns coordinating ground and space-based telescopes will gradually fill in the gaps. We'll learn what 3I-ATLAS is made of, how it's outgassing, and whether its chemistry truly deviates from known cometary patterns, or just represents a normal variation we haven't sampled well before. But for now, the green glow remains both answer and question. It tells us chemistry is happening, confirms the object is active, provides evidence consistent with cometary composition, and simultaneously it highlights how much we don't know, how unusual the emission patterns appear, how the visual evidence doesn't quite match the physical predictions. The green says comet in one language while everything around it whispers something else in another. If 3I-ATLAS is indeed a comet, it's teaching us that interstellar comets might be fundamentally different from their solar system cousins. They've been cooked by different suns, aged in the radiation bath of interstellar space, and potentially modified by passage through environments we've never studied. Their chemistry might be alien not because it's artificial, but because it reflects planetary system chemistry from another star, compositions that don't exist in our small sample of solar system objects. The green isn't evidence of life or technology, it's evidence of diversity, of cosmic variety that challenges our neat categories. Or maybe, just maybe, the green is exactly what we think it is, and everything else about 3I-ATLAS is what's genuinely strange. Maybe the chemistry is normal, but something about the object's structure, composition, or behaviour is not. Maybe we're focusing on the green because it's familiar while ignoring clues in the missing dust, the unusual acceleration, the clean morphology that collectively point towards something we don't have a framework to recognise yet. The green glow is a comfort and a taunt. It lets us classify 3I-ATLAS as a comet with confidence, checking a box, filing it in the proper category. But every time we look at that brilliant emerald light in the images, we're reminded of all the other boxes that remain empty, all the expected features that aren't there, all the ways this object refuses to be typical. The green says yes, it's a comet. The rest of the evidence asks, are you sure? Part 5. The Astronomer's Dilemma. Classification in science isn't just bureaucratic bookkeeping. It's how we organise knowledge, test theories, and communicate about what we've discovered. When astronomers call something a comet, that label carries implications: icy composition, volatile outgassing, development of coma and tail, predictable behaviour near the sun. When they call something an asteroid, different implications follow: rocky or metallic composition, minimal volatiles, stable appearance regardless of solar distance. These categories evolved over centuries of observation, refined as we learned more about small bodies in our solar system. They work well for the objects that defined them. The question now is whether they work for 3I-ATLAS. Scientists at the Jet Propulsion Laboratory, which tracks near-Earth objects and calculates orbits for anything that might pose a threat, have the unenviable task of classifying new discoveries. When 3I-ATLAS was first detected, they had to decide, comet or asteroid. The initial observations showed activity, a coma, suggesting volatile material. That pointed to comet. The orbit was clearly hyperbolic, meaning the object originated outside the solar system. That added the prefix I for interstellar. So officially, 3I-ATLAS became an interstellar comet, joining 2I/Borisov in that exclusive category. Case closed, right? Except the more data that came in, the more uncomfortable that classification became. Yes, there's activity. Yes, there's the green glow of C2 emission, but the morphology doesn't match expectations. The tail behaviour is anomalous. The acceleration to dust ratio seems wrong. 3I-ATLAS checks some comet boxes while leaving others conspicuously empty. It's like trying to classify an animal that has fur like a mammal, lays eggs like a reptile, and has a duck's bill. You can force it into a category, but you're aware the category isn't capturing the whole truth. Avi Loeb, the Harvard astronomer who led the controversial Galileo project to search for evidence of extraterrestrial technology, has been vocal about 3I-ATLAS not fitting cometary norms. He points to the missing tail despite observed acceleration as evidence that natural explanations require increasingly elaborate assumptions. Loeb argues that at some point, the number of special conditions needed to explain an object naturally exceeds the complexity of considering artificial origins. This is a philosophical stance as much as scientific. When do we allow ourselves to seriously consider non-natural explanations? How many anomalies constitute a pattern rather than coincidence? Most astronomers push back strongly against this reasoning. The history of astronomy is filled with observations that seemed inexplicable until better data or better models arrived. Pulsars, as mentioned earlier, aren't alien beacons but natural astrophysical objects. Fast radio bursts weren't extraterrestrial signals but magneta activity. Every time we've encountered something strange in the cosmos, the answer has eventually been natural, often teaching us new physics in the process. Why should 3I-ATLAS be different? The safer, more scientific approach is to assume natural processes until absolutely proven otherwise. But there's a subtle shift happening in the astronomical community's discourse around interstellar objects. 1I/Oumuamua forced scientists to confront how little they knew about what such objects should look like. Before 2017, interstellar visitors were theoretical, predicted by simulations but never observed. Oumuamua's weirdness couldn't be dismissed because we had no baseline for normal. 2I/Borisov reassured us by looking cometary, fitting expectations. Now 3I-ATLAS sits between those extremes, active like Borisov but morphologically odd like Oumuamua. This pattern suggests maybe we need a new classification scheme entirely. Perhaps interstellar comet and interstellar asteroid are insufficient categories, imposing solar system taxonomy onto objects that don't share solar system history. Interstellar objects might deserve their own classification system based on different criteria: origin star system characteristics, interstellar exposure history, composition reflecting different stellar nebulae chemistry. The current labels might be causing more confusion than clarity, forcing square pegs into round holes. The European Southern Observatory, which operates some of the most powerful telescopes in the Southern Hemisphere, issued statements acknowledging the unusual nature of 3I-ATLAS, while cautioning against premature conclusions. Their position represents the scientific mainstream: document the anomalies, pursue natural explanations vigorously, but avoid spectacular claims without spectacular evidence. This conservatism is appropriate. Science progresses by careful accumulation of evidence, not by jumping to exciting conclusions. Yet, even conservative astronomers admit the classification is strained. In private conversations at conferences, away from press releases and official statements, researchers express uncertainty about what 3I-ATLAS really is. The word comet gets used with hedges and qualifications. Papers describe it as an active interstellar object with cometary characteristics, rather than simply an interstellar comet. The language betrays discomfort, an awareness that the label doesn't quite fit, but no better alternative exists yet. The implications extend beyond semantics. If our taxonomies fail for interstellar objects, what does that mean for our understanding of planetary system formation in general? Solar system comets and asteroids tell us about the conditions in our protoplanetary disk 4.5 billion years ago. Interstellar visitors should tell us about conditions in other systems, providing comparative data to test formation theories. But if we can't even reliably classify these objects, how can we interpret what they're teaching us? There's also the planetary protection angle. Though 3I-ATLAS poses no collision risk with Earth, maintaining healthy distance of around 1.8 astronomical units at closest approach, the interest from space agencies is significant. NASA and ESA both monitor interstellar visitors for scientific opportunity, and implicitly to assess whether such objects could ever pose threats. If interstellar visitors don't behave predictably, if they have propulsion capabilities or unusual trajectories, that complicates risk assessment. Most scientists consider this remote concern, but it's discussed in planning documents nonetheless. The deeper philosophical question lurking behind the classification dilemma is whether we're observers or witnesses. Are we observing a comet, an icy body following natural physical laws that we'll eventually understand with better data? Or are we witnessing something that challenges the natural versus artificial boundary, something that might be a product of intelligence rather than mere stellar ejection? Most astronomers firmly believe the former. A small but vocal minority, including Loeb, argue the latter deserves serious scientific investigation rather than dismissal. This tension isn't new. SETI, the Search for Extraterrestrial Intelligence, has spent decades scanning for radio signals that might indicate alien technology. The assumption underlying SETI is that intelligence expresses itself through deliberate communication. But what if intelligence also expresses itself through artifacts, probes, or engineered objects sent between stars? The Galileo project, launched in part by Loeb after the Oumuamua controversy, seeks to search for physical evidence of extraterrestrial technology, including anomalous interstellar objects. 3I-ATLAS might factor into this search whether astronomers like it or not. Its anomalies, while individually explainable through natural mechanisms, collectively create a profile that stands out. If you were designing a screening algorithm to flag interesting interstellar objects for follow-up, 3I-ATLAS would trigger multiple criteria: unusual acceleration, missing expected tail, intense emission without proportional dust, clean morphology. None of these definitively indicate artificiality, but together they warrant attention. What observations would resolve the classification? High-resolution imaging that reveals surface features, if any exist. Detailed spectroscopy measuring isotopic ratios. Different stellar environments produce different isotope abundances, so measuring deuterium to hydrogen or carbon 13 to carbon 12 ratios could constrain the object's origin system. Detection of refractory dust that's definitely not from our solar system would confirm interstellar origin beyond doubt while testing compositional models. And ideally, a spacecraft mission, though the object's speed and trajectory make that nearly impossible with current technology. There's a watch list developing in the astronomical community. As 3I-ATLAS continues moving away from the Sun and viewing geometry improves, certain observations would tip the balance toward natural versus highly anomalous. If a conventional dust tail emerges, most mysteries resolve. If none appears despite favourable geometry, the object becomes genuinely difficult to explain naturally. If spectroscopy reveals completely unexpected molecular species or ratios, that challenges formation models. If high-resolution images show any hint of structure or non-natural geometry, that changes everything. The astronomer's dilemma is this: how do you remain scientifically rigorous while acknowledging genuine anomalies? How do you avoid both the trap of premature speculation and the trap of stubborn orthodoxy that ignores real puzzles? 3I-ATLAS sits right in that uncomfortable middle zone where it's strange enough to be interesting, but not strange enough to overturn paradigms. It's in limbo, classified but not understood, labelled but not explained. Part of the difficulty is cultural. Astronomy has developed strong norms around conservatism precisely because the field has a history of spectacular claims that didn't pan out. When Percival Lowell claimed to see canals on Mars, it was taken seriously for decades before better observations proved them illusory. When pulsars were discovered, the little green men hypothesis was briefly entertained but quickly abandoned for natural explanations. Scientists learned to be cautious, to favour mundane explanations, to require extraordinary evidence for extraordinary claims. This conservatism serves the field well most of the time, but there's risk in being too conservative. If 3I-ATLAS genuinely is something unprecedented, if its anomalies are trying to tell us something important about interstellar objects, or even about the possibility of artificial objects in space, dismissing it prematurely as just a weird comet could cause us to miss crucial insights. The history of science also includes examples of real discoveries initially dismissed because they didn't fit prevailing theories. Continental drift, ball lightning, even meteorites were once considered fringe ideas before evidence became overwhelming. So the classification dilemma isn't just about what to call 3I-ATLAS. It's about how science handles genuinely ambiguous cases, objects that resist easy categorization, observations that don't cleanly confirm or refute existing theories. Do we force-fit them into existing boxes and move on? Do we create new categories that might be premature? Do we leave them unclassified, admitting uncertainty? For now, 3I-ATLAS remains officially an interstellar comet, with that designation carrying increasingly obvious caveats. As Act 2 of this investigation unfolds, we'll widen our lens to compare this object with previous interstellar visitors, explore alternative physical mechanisms that might explain its behaviour, and confront the possibility that our understanding of what can exist in interstellar space might be incomplete. The classification question won't be settled soon, but asking it forces us to examine our assumptions, test our models, and remain open to surprises from the cosmos. What do we call something that looks almost like a comet but refuses to completely behave like one? Whatever we decide, the label matters less than the investigation it sparks. 3I-ATLAS, whatever it ultimately is, has already succeeded in making astronomers uncomfortable, and that discomfort is often where science makes its most interesting discoveries. Part 6. Lessons from Oumuamua. October 19th, 2017. Astronomers using the Pan-STARRS telescope in Hawaii noticed something that shouldn't have been possible. An object moving through the inner solar system on a hyperbolic trajectory, meaning it wasn't gravitationally bound to the Sun. It came from elsewhere, passed through our neighbourhood, and was leaving forever. The discovery was breathtaking. For the first time in human history, we had detected a visitor from interstellar space, an actual physical object from another star system. They named it 1I/Oumuamua, Hawaiian for scout or messenger, the first of its kind. The excitement lasted about 5 minutes before confusion set in. Oumuamua didn't look like anything astronomers expected. Initial observations suggested it was highly elongated, perhaps 10 times longer than it was wide, tumbling through space like a cosmic cigar. This shape was unprecedented. No asteroid or comet in our solar system has proportions that extreme. Subsequent analysis refined the shape estimates, but the strangeness remained. This object was weird in fundamental ways that challenged comfortable categories. Then came the acceleration problem. Like 3I-ATLAS, Oumuamua displayed non-gravitational acceleration, deviating from the trajectory gravity alone would predict. For a comet, this would be normal, explained by outgassing. But Oumuamua showed no visible coma, no dust tail, no gas emissions detectable by any instrument. It looked like an asteroid, inert and inactive. Yet it accelerated like a comet. Astronomers were forced to explain rocket-like behaviour without the rocket, thrust without propellant, acceleration without visible mechanism. The similarity to 3I-ATLAS becomes immediately apparent. Both objects show acceleration. Both lack obvious tails or extensive dust. Both force scientists into uncomfortable positions of proposing exotic explanations for seemingly straightforward observations. The difference is that Oumuamua showed no activity at all, no green glow, no coma, while 3I-ATLAS shows activity but not the expected consequences. It's like Oumuamua was all mystery, while 3I-ATLAS is half conventional and half mystery, which somehow makes it more frustrating. One explanation for Oumuamua's behaviour involves hydrogen outgassing. The hypothesis, developed by several research teams, suggests the object could have been rich in molecular hydrogen ice, formed in the extreme cold of interstellar space. As it approached the Sun and warmed, this hydrogen sublimated, producing thrust. Crucially, hydrogen outgassing would be completely invisible to optical telescopes. No dust, no coloured emissions, nothing to see. The object would appear inert while actually venting gas vigorously enough to alter its trajectory. Could this apply to 3I-ATLAS? Possibly, but with complications. 3I-ATLAS shows visible activity through its green C2 emission. suggesting at least some traditional cometary chemistry is happening. If hydrogen outgassing is also occurring, it would be in addition to, not instead of, the C2 producing processes. This creates a hybrid scenario, some conventional outgassing producing the green glow, plus invisible hydrogen outgassing providing most of the acceleration. It's not impossible, but it requires two different mechanisms operating simultaneously, which feels like doubling our assumptions to fit the data. The other famous hypothesis about Oumuamua comes from Avi Loeb himself. In a paper that sparked enormous controversy and media attention, Loeb and colleagues proposed that Oumuamua's unusual acceleration could be explained if the object were an artificial light sail, a thin reflective sheet designed to use sunlight for propulsion. Light sails are a real concept in spacecraft design. Photons carry momentum, and a large, lightweight reflective surface can be pushed by sunlight. If Oumuamua were essentially a giant mirror, its acceleration would follow naturally from physics without requiring any fuel or outgassing. The light sail hypothesis was and remains deeply controversial. Most astronomers consider it unnecessarily speculative, an exotic explanation proposed before natural alternatives were exhausted. The scientific pushback was intense. Critics pointed out that natural fragmentation could produce unusual shapes, that hydrogen outgassing provided a plausible mechanism, that invoking aliens should be a last resort, not an early suggestion. Loeb countered that science should consider all possibilities without prejudice, that the artificial hypothesis was testable and deserved examination alongside natural ones. Applying similar logic to 3I-ATLAS immediately raises questions. If it were an artificial object, why does it show green C2 emission, which seems naturally cometary? A manufactured light sail or probe wouldn't necessarily outgas organics unless it was covered in natural ice or deliberately designed to mimic a comet. But if you're building an interstellar probe, why make it look like a comet? What's the advantage? You might argue camouflage. An artificial object disguised as natural would escape scrutiny. But that requires attributing deceptive intent to hypothetical aliens, which is pure speculation piled on speculation. What Oumuamua taught the astronomical community is that interstellar objects aren't necessarily copies of solar system objects. They might come in varieties we haven't imagined because they formed under different conditions, experienced different histories, or represent physical regimes we don't have local examples of. Oumuamua forced scientists to expand their thinking about what small bodies can be. It generated hypotheses about hydrogen ices, extreme shapes, surface properties, all driven by necessity to explain observations. 2I/Borisov, discovered in August 2019, provided a counterpoint. It looked like a comet, acted like a comet, displayed prominent dust and gas tails. Spectroscopy revealed water vapour, carbon monoxide, cyanide, exactly what you'd expect. Its nucleus was estimated around 0.5 kilometre across. Its coma was textbook. Astronomers collectively sighed with relief. Apparently interstellar comets could be normal. Oumuamua might have been the outlier, the weird one, and Borisov represented the expected baseline. 3I-ATLAS now occupies a middle position. It has Borisov's activity and cometary signatures, but some of Oumuamua's morphological oddness, an unexplained acceleration to visible outgassing mismatch. It's as if the cosmos is deliberately showing us a spectrum, fully anomalous with Oumuamua, fully conventional with Borisov, and now something in between with 3I-ATLAS. The question is whether this represents natural variation, interstellar objects simply come in many forms, or whether we're seeing fundamentally different classes of object, some natural, and perhaps others not. Creating a hypothetical comparison helps clarify what we'd expect. If 3I-ATLAS is a natural comet, albeit with unusual composition, we'd predict its isotopic ratios should match, planetary formation models, its dust-to-gas ratio might be low but not zero, its acceleration should correlate directly with observed mass loss even if the mechanism is exotic like hydrogen outgassing. And over time as geometry improves, a faint tail should emerge. These are testable predictions. If 3I-ATLAS were an artificial probe, we might expect precisely controlled trajectory changes rather than variable outgassing-driven acceleration, possible structural features detectable in high-resolution imaging, non-equilibrium composition showing elements or molecules that don't naturally coexist, and perhaps emission signatures at radio or infrared wavelengths indicative of power systems or internal processes. These are also testable, though much harder to confirm without close-up investigation. The reality is neither hypothesis is currently well supported by decisive evidence. We have an anomalous object with properties that strain natural explanations without clearly breaking them. The lesson from Oumuamua is that anomalous doesn't mean artificial, but it does mean we should pay attention, gather data, and avoid dismissing puzzles prematurely. One interesting aspect of comparing these three interstellar visitors is their arrival rate. Before 2017, the consensus was that interstellar objects must pass through the solar system regularly, but remain undetected because they're small and fast-moving. Discovering 1I/Oumuamua confirmed this, and suggested detection rates would increase as telescope surveys improved. 2I/Borisov, arriving just 2 years later, supported that prediction. Now 3I-ATLAS continues the trend. We're beginning to accumulate a sample size, small but growing. If interstellar visitors are common, their diversity becomes interesting data. Are they all comets from ejected Oort cloud-like reservoirs around other stars? Are some asteroids from fragmented planets? Could any be artificial? The sample is too small for statistics yet, but patterns might emerge. If every interstellar object shows weird features, that suggests something about interstellar space itself, some environmental factor that modifies all small bodies travelling between stars. If only some are weird, that suggests intrinsic differences in their origins. Oumuamua's tumbling motion was another oddity worth comparing. The object rotated with a period of around 8 hours, and the tumbling seemed complex, not simple rotation around a single axis. Some models suggested it was tumbling chaotically, possibly due to outgassing jets creating torque. 3I-ATLAS's rotation hasn't been definitively measured yet, partly because it's fainter and harder to observe. But if rotation data becomes available, comparing tumbling behaviour might reveal whether outgassing patterns or internal structure similarities exist between these objects. The takeaway from Oumuamua's legacy is caution paired with curiosity. Caution because the alien speculation, while generating public interest, also created backlash and made some scientists reluctant to engage with genuinely interesting questions about the object. Curiosity because Oumuamua opened a door to a new field of study, interstellar object science, that didn't really exist before 2017. Now we have techniques, dedicated searches, and theoretical frameworks specifically for understanding visitors from other star systems. 3I-ATLAS benefits from this prepared context. Astronomers know to look for non-gravitational acceleration. They know to check for unusual shapes or morphologies. They know interstellar objects might not fit comfortable categories. The infrastructure exists now to mount comprehensive observation campaigns, to coordinate multiple telescopes, to bring diverse expertise together. Oumuamua was discovered almost by accident and escaped before we could study it thoroughly. 3I-ATLAS is being tracked intensively, with every available resource pointed at it during its passage. But the fundamental question remains the same. What are we looking at? Oumuamua never answered that question definitively. It left the solar system trailing mysteries and hypotheses, but no consensus. Borisov seemed to answer it. Just a comet, but that might have been false reassurance, a single data point that doesn't represent the population. 3I-ATLAS is our third chance to understand what interstellar space sends us. Will it finally provide clarity, or will it add more layers to the confusion? The spectrum of possibilities grows with each discovery. Maybe interstellar objects are simply diverse, reflecting the diverse planetary systems they come from. Maybe some are processed by interstellar conditions in ways that make them look artificial without being so. Maybe a small fraction actually are artificial, probes or debris from technological civilizations, and we lack the framework to recognize them yet. Or maybe, as most scientists believe, they're all natural, just stranger than the limited sample in our solar system led us to expect. Oumuamua taught us to expect the unexpected. Borisov taught us not to overinterpret single cases. 3I-ATLAS is teaching us that the universe doesn't hand us easy answers, that mysteries can persist even with good data, and that sometimes the most honest position is acknowledging uncertainty while continuing to investigate. The lessons accumulate, but the final exam hasn't been given yet. Part 7. The Geometry Trap. Understanding what we're seeing requires understanding where we're standing. Observational astronomy isn't like laboratory science where you can manipulate your subject, viewing it from every angle under controlled conditions. When we observe comets, we're stuck with a single vantage point. Earth or Earth orbit, watching objects millions of miles away from a perspective we can't change. Geometry matters enormously. The alignment of Sun-object Earth determines what features become visible and which remain hidden. 3I-ATLAS's missing tail might be the greatest disappearing act in cometary science, or it might just be pointing directly at us, invisible due to foreshortening. Imagine you're photographing a javelin thrown across a field. If you stand perpendicular to the throw, you see the full length of the javelin's flight, its trajectory clear in your frame. But if you stand directly in line with the throw, the javelin appears as a small dot approaching or receding, its length compressed by perspective. Comets work similarly. The tail, which can stretch millions of miles, becomes a small glow around the nucleus when viewed head-on because all that length is compressed into our line of sight. On November 5th, 2025, 3I-ATLAS sat at specific coordinates in three-dimensional space, 1.38 astronomical units from the Sun, 2.23 astronomical units from Earth. But those distances alone don't tell the full geometric story. What matters is the angle. Solar elongation, the angle between the Sun and the object as seen from Earth, was approximately 10 to 13 degrees. For reference, your fist held at arm's length covers about 10 degrees of sky. 3I-ATLAS was basically one fist width away from the Sun in our view. This geometry is terrible for tail detection. Any dust tail points away from the Sun due to radiation pressure. With the Sun almost directly behind Earth in our perspective, that tail points toward us, compressed into a small angular area around the nucleus. It would appear as enhanced brightness in the coma rather than a distinct tail structure. This is well understood in cometary science. Observers know that solar elongations below 15 or 20 degrees make tail morphology difficult to study. The geometry is simply unfavourable. But here's where the trap closes. While geometry can hide a tail, it can't completely erase brightness. If 3I-ATLAS has a dust tail comparable to similar-sized comets post-perihelion, even foreshortened, it should contribute measurable flux to the coma region. The total amount of sunlight scattered by the dust doesn't change based on our viewing angle, just its distribution in our images. A bright dust-rich tail seen from the side appears as an elongated structure. The same tail viewed head-on appears as concentrated brightness around the nucleus. The November 5th image shows neither, no elongation and relatively modest brightness given the expected dust content. The Hubble Space Telescope's July 21st observation, months before perihelion, adds crucial context. That image captured 3I-ATLAS at a different geometry, different distance, different phase of its approach. Hubble revealed a teardrop-shaped dust cocoon, asymmetric and complex. This wasn't a classic tail, but it demonstrated dust was present and distributing in peculiar ways. Some astronomers interpreted the teardrop as an early-stage tail, others as a cocoon of material not yet fully blown back by solar radiation. Interestingly, Hubble also showed what appeared to be an anti-tail effect, material appearing sunward of the nucleus. Anti-tails aren't actual reverse tails, but optical illusions created by large dust particles that lag behind the comet in its orbit. Because they move slower, they fall slightly behind the nucleus. When viewed from certain angles, specifically when Earth crosses the comet's orbital plane, these lagging particles appear projected sunward, creating the illusion of a tail pointing the wrong direction. The effect is well documented in solar system comets and indicates substantial dust is present, but distributed three-dimensionally rather than in a simple linear tail. If 3I-ATLAS's dust is forming shells, cocoons, or complex three-dimensional structures rather than a flat tail, that complicates the geometry story significantly. Foreshortening explanations assume a linear tail that gets compressed when viewed head-on. But if the dust distribution is already non-linear, forming asymmetric clouds or shells, then viewing angle alone doesn't explain what we're seeing. You'd need to explain why the dust distribution is unusual in the first place. Think of it this way. Geometry can hide a normal tail, but it can't create abnormal dust dynamics. If 3I-ATLAS's dust is behaving strangely, forming cocoons instead of tails, distributing asymmetrically, concentrating in unexpected regions, that's evidence of unusual physics or composition regardless of viewing angle. Geometry becomes an excuse that stops working once retriem continue you examine it closely. The object might have unusual dust dynamics hidden by geometry, which means the geometry isn't solving the mystery, just obscuring additional weirdness. Forward scattering adds another layer of complexity. When sunlight hits dust particles, it doesn't scatter equally in all directions. Tiny particles forward scatter preferentially, meaning they reflect more light in the direction the light was already travelling. If we're looking at 3I-ATLAS with the sun behind us, dust particles in a tail pointing toward us would forward scatter sunlight, potentially making them brighter than we'd expect from simple geometric calculations. Conversely, if the particles are larger, or the geometry is slightly off, the scattering could work against visibility. The math becomes complicated, requiring detailed models of particle size distributions and scattering cross-sections. Some researchers have suggested the dust grains might be exceptionally small, on the order of micrometers or smaller. Extremely fine dust behaves differently than typical cometary dust. It gets accelerated more efficiently by radiation pressure because of favourable surface area to mass ratios. These tiny particles would be swept away from the nucleus rapidly, dispersing into space before forming a concentrated tail. The result would be a diffuse, faint dust component that's hard to detect even under good viewing conditions. But this hypothesis requires explaining why 3I-ATLAS produces preferentially small dust grains, which brings us back to compositional or structural peculiarities. There's also the possibility of rapid sublimation. If dust grains are icy rather than rocky, they might sublimate quickly after ejection, essentially evaporating before they can travel far from the nucleus. This would create a situation where outgassing produces dust, the dust briefly exists and scatters light near the nucleus, but then disappears before forming a traditional tail. You'd see enhanced coma brightness, but minimal tail structure. However, this requires the dust to be unusually volatile, made of materials that sublimate easily, which again implies unusual composition. As months pass and 3I-ATLAS moves farther from the Sun, the geometry from Earth changes. The solar elongation increases as the object's position relative to the Sun and Earth evolves. By late 2025 and into 2026, viewing angles should become much more favourable. The Sun-object-Earth angle will open up, reducing foreshortening effects. If there's a tail hidden by geometry, this is when it should reveal itself. Observers worldwide are watching specifically for this emergence, comparing images over time to detect any elongation or asymmetry that wasn't visible during the unfavourable geometry of November. This makes 3I-ATLAS a live experiment unfolding in real time. Every few weeks brings new observations, new viewing angles, new opportunities to detect the missing tail if it exists. The scientific community is essentially betting on one of two outcomes. Either the tail gradually emerges as geometry improves, vindicating the hidden by foreshortening explanation and allowing everyone to relax, or the tail remains absent even under favourable geometry, forcing serious reconsideration of what this object is. But there's a third possibility that's more subtle and potentially more troubling. What if a tail partially emerges, but it's still weaker, smaller and stranger than models predict? What if geometry was hiding some tail structure, but once revealed that structure doesn't match expectations? You could have both things true simultaneously. Geometry was a factor, and the object is genuinely anomalous. This middle ground scenario would be harder to interpret because it would validate the geometric explanation partially, while still leaving fundamental questions unanswered. Instrumental factors also matter. Different telescopes observe in different wavelength bands with different sensitivities. Narrow band filters tuned to specific emission lines reveal chemical features but might miss broad spectrum reflected light from dust. Wideband filters capture more total light but lack spectral detail. The November 5th image used specific filters optimized for detecting C2 emission, which is why the green glow is so prominent. But those same filters might not be ideal for detecting faint extended dust tails. Other observations with different instrumentation might reveal structures invisible in the November image. Integration time, the length of exposure, dramatically affects what faint features become visible. Long exposures can reveal extended low surface brightness structures that disappear in shorter exposures. The trade-off is that longer exposures can saturate the bright nucleus, making it harder to study the immediate coma. Balancing these factors requires observation strategies tailored to specific science questions. Some campaigns focus on the nucleus and inner coma, others on extended tail structure. 3I-ATLAS is being observed with various integration times and filters, building a multi-dimensional dataset that should eventually reveal the full picture. Consider also that our Earth-based view is temporally constrained. We can only observe when the object is above our horizon, when weather permits, when telescope time is available. This creates gaps in coverage. If 3I-ATLAS's dust production varies over time, perhaps with rotation of the nucleus exposing different surface regions, or with distance from the Sun affecting sublimation rates, our snapshots might miss peak activity or unusual events. Continuous monitoring from multiple longitudes helps, but doesn't eliminate the problem. Space-based observatories like Hubble solve some problems while creating others. Hubble has exceptional resolution and stable viewing conditions without atmospheric interference, but its observing schedule is precious and oversubscribed. 3I-ATLAS gets allocated time, but not continuous coverage. The July image and subsequent observations provide crucial data points, but can't track changes hour by hour or day by day. You're sampling the object's behaviour, not watching it continuously, which means transient phenomena might be missed entirely. The geometry trap is that it offers scientists a comfortable explanation that's difficult to definitively rule out until better viewing conditions arrive. It allows the community to say, "Let's wait and see," rather than confronting potentially disturbing conclusions. This isn't dishonest. Patience is scientifically appropriate when dealing with ambiguous data. But it does create a psychological escape hatch, a way to defer difficult questions about whether 3I-ATLAS truly is anomalous or just poorly viewed. There's historical precedent for geometry causing confusion. Comet Encke, for instance, showed unusual behaviour in the 19th century that puzzled observers before better understanding of non-gravitational forces, and viewing geometry resolved the mystery. Comet Halley's appearances have varied dramatically depending on viewing geometry, sometimes spectacular and sometimes disappointing. Geometry has always been a confounding factor in cometary science, which is why modern astronomers are cautious about overinterpreting single observations from unfavourable angles. But 3I-ATLAS has the advantage of being observed by an unprecedented array of instruments with sophisticated modelling capabilities. We can simulate what the object should look like from our viewing angle, under various assumptions about tail properties. These forward models, comparing predictions to observations, help constrain what's actually there versus what's hidden. If models consistently fail to match observations even after accounting for geometry, that's strong evidence the problem isn't just viewing angle. Some researchers have created hypothetical scenarios showing what 3I-ATLAS should look like from the November 5th geometry if it had various types of tails: dust-rich, gas-rich, mixed, different particle size distributions. By comparing these simulations to actual images, they can rule out certain scenarios. A massive dust-rich tail like Comet Hale-Bopp would still be visible even foreshortened. A pure gas tail might be invisible. The actual observations fall into a narrow range that's consistent with either minimal dust or severely geometrically constrained viewing, and teasing apart those possibilities requires additional data. The anti-tail phenomenon seen in Hubble's earlier imagery provides a clue. Anti-tails appear when we view comets nearly edge on to their orbital plane, seeing lagging dust particles projected against the sky. This confirms substantial dust was present months ago. If that dust continued to be produced through perihelion, it should still be present now, trailing behind the nucleus. The question is whether current viewing geometry simply hides it, or whether something changed post-perihelion that reduced dust production. One possibility is that 3I-ATLAS's nucleus is rotating, and the active regions that produce dust were facing different directions pre- and post-perihelion. If outgassing is localized to specific jets or patches rather than globally distributed, and if those jets happen to be pointed in directions that don't produce visible tails from our current viewing angle, that could explain the observations. But this is getting complicated, requiring multiple assumptions to stack. Localized jets, plus specific orientations, plus unfavourable geometry, all combining to hide the tail. It's possible, but feels increasingly contrived. The geometry trap is ultimately a test of patience and methodology. Science requires waiting for better data rather than leaping to conclusions. 3I-ATLAS will reveal more of itself over coming months as viewing angles improve. The tail mystery will resolve one way or another. Either we'll see emergence of structures confirming the object is a normal comet viewed badly, or we'll see continued absence of expected features forcing deeper reconsideration. But while we wait for geometry to improve, other lines of investigation continue, We don't have to put everything on hold pending better viewing angles. Spectroscopy, thermal observations, comparative studies with other interstellar objects, theoretical modelling of exotic compositions, all of these proceed in parallel. Geometry might hide the tail, but it can't hide everything. The acceleration is measurable regardless of viewing angle. The green emission is detectable. The overall brightness and morphology are documented. These are real data points that need explanation whether or not the tail eventually appears. Perhaps the most honest position is acknowledging that geometry probably is a factor, likely is hiding some tail structure, but almost certainly isn't the complete explanation. 3I-ATLAS probably has unusual dust dynamics in addition to being viewed from an unfavourable angle. Both things can be true. The danger is using geometry as a universal excuse, a way to avoid confronting genuinely strange aspects of the object by attributing everything to perspective effects. We're trapped between two interpretations, and only time will spring the trap. If the tail emerges, we'll know geometry was the culprit, and 3I-ATLAS will be downgraded from genuinely weird to transiently confusing. If the tail stays missing, we'll know something deeper is wrong with our understanding, and the object will demand serious theoretical attention. For now, we're stuck in the trap, simultaneously constrained by unfavourable viewing and uncertain whether what we're seeing is illusion or reality. The geometry might be hiding a comet, or it might be hiding something far stranger that merely resembles a comet in some ways, while breaking the mould in others. Part 8. Hidden Forces and Plasma Theories. The space between the Sun and its planets isn't empty. It's filled with a flowing stream of charged particles, protons and electrons mostly, blown outward from the Sun's corona at speeds approaching 1,000,000 miles per hour. We call this the solar wind, and it's not a gentle breeze, it's a supersonic plasma, a fourth state of matter where atoms are ionized into free electrons and nuclei, carrying magnetic fields and electrical currents. When this wind encounters a comet, the interaction is complex, violent, and still not fully understood despite decades of study. Traditional cometary science focuses on radiation pressure, the momentum carried by sunlight itself. Photons streaming from the sun push against dust particles, physically shoving them away from the comet and creating the classic dust tail. This is mechanical, straightforward, calculable. But the solar wind adds electromagnetic effects that are subtler and harder to model. Dust grains in a comet's coma can become electrically charged through photoionization, solar ultraviolet light knocking electrons off atoms. Once charged, these grains respond to electric and magnetic fields, not just radiation pressure. The Lorentz force, familiar from undergraduate physics, describes how charged particles move in electromagnetic fields. A charged dust grain in the solar wind experiences forces perpendicular to both the wind direction and the magnetic field direction, causing it to spiral or deflect rather than simply being blown straight back. For typical solar system comets with heavy dust production, these electromagnetic effects are minor compared to radiation pressure. But for an object like 3I-ATLAS, with seemingly minimal dust and unusual morphology, electromagnetic forces might matter more than we usually account for. Recent data from the Parker Solar Probe, which has been diving closer to the Sun than any spacecraft in history, reveals that the near-Sun environment is more electrically and magnetically active than previous models assumed. The solar wind isn't uniform but filled with structures, current sheets, magnetic switchbacks, plasma waves. At one point, 3.8 astronomical units, where 3I-ATLAS passed through perihelion, the solar wind has cooled and expanded compared to its source at the Sun's corona, but it's still dynamic and structured. A comet passing through might encounter varying conditions that affect dust dynamics in ways standard models don't capture. What if 3I-ATLAS's dust grains are unusually small and easily charged? The surface area to mass ratio matters enormously for how particles respond to forces. Tiny grains, micron-sized or smaller, charge up quickly and respond strongly to electric fields. If the object is producing predominantly small dust, rather than the mix of sizes typical in solar system comets, those grains might be deflected or dispersed by electromagnetic forces in ways that suppress visible tail formation. The dust would still be ejected, accounting for the observed mass loss and acceleration, but its distribution in space could be fundamentally different from what radiation pressure alone predicts. There's also the question of dust grain composition. If 3I-ATLAS's dust is carbonaceous rather than silicate-dominated, its electrical properties differ. Carbon can be semiconducting or even conducting depending on structure. Graphitic or amorphous carbon grains would interact with plasma differently than rocky particles. They might align with magnetic fields, cluster through electrostatic attraction, or even emit secondary electrons under solar wind bombardment. These effects could alter the optical properties and spatial distribution of the dust, making it harder to detect in standard observations. Plasma instabilities provide another potential mechanism. When a comet's outgassing creates a neutral gas cloud, the solar wind ploughs into this obstacle, creating a shock and draping magnetic field lines around the coma. This interaction can drive plasma instabilities, waves and turbulence that accelerate some particles while decelerating others. The effect is to create a complex plasma environment immediately around the comet, where normal rules about dust behavior might not apply. Dust grains caught in these regions could experience forces that scatter them diffusely, rather than concentrating them into a tail. The Parker Solar Probe's observations of magnetic switchbacks are particularly intriguing. These are sharp reversals in the solar wind's magnetic field direction, occurring on scales of seconds to minutes. Their origin is still debated, but they're common in the inner heliosphere. If 3I-ATLAS encountered a region rich in switchbacks during or just after perihelion, the fluctuating magnetic fields could have affected charged dust in unpredictable ways. The dust might have been accelerated in multiple directions, dispersed radially rather than forming a coherent tail structure. Consider also the possibility of sputtering. When high-energy solar wind ions strike dust grains, they can knock atoms off the surface, gradually eroding the particles. For very small grains, sputtering could destroy them entirely before they travel far from the nucleus. This would create a situation where dust is continuously produced but also continuously destroyed, maintaining a thin, steady-state coma without a building up a long-lasting tail. The equilibrium between production and destruction would depend on grain size, composition and solar wind conditions, all of which might be different for an interstellar object compared to solar system comets. There's a more speculative idea involving magnetic dust. Some theoretical work suggests dust grains could become magnetized through various processes, acquiring permanent or induced magnetic moments. Magnetized dust in the solar wind's magnetic field would experience additional forces that could cause unusual behavior. This is far from mainstream cometary science, but for an object as strange as 3I-ATLAS, exploring unconventional mechanisms seems justified. What about electrostatic levitation? Laboratory experiments have shown that charged dust particles on surfaces can levitate due to electrostatic repulsion when illuminated by ultraviolet light. On an airless body like a comet nucleus, charged dust grains might hover above the surface or be ejected more easily than uncharged grains. This could enhance dust production in some ways while altering the initial velocity distribution, potentially affecting how tails form. Again, this is speculative applied to comets, but the physics is real and could matter for objects with unusual surface properties. The concept of a dust-free outgassing regime deserves deeper examination. What if the volatile gases escaping from 3I-ATLAS are simply not entraining much dust? Gas molecules can escape individually through pores and cracks, without dragging solid particles along. If the nucleus has a porous structure, or if sublimation is happening primarily from subsurface layers, with gas percolating outward, dust production might be naturally suppressed. The gas carries momentum and produces acceleration, but without dust the tail is invisible or minimal. This is a compositional explanation, but with physical consequences that plasma effects could enhance. Some researchers have modelled scenarios where intense localized jets, rather than distributed outgassing, dominate a comet's activity. Jets can be so collimated and fast that they disperse dust quickly before it forms a traditional tail. If 3I-ATLAS has a few strong jets oriented in specific directions, and if plasma effects further disperse the dust they eject, you could get the observed combination of acceleration without prominent tail. But this requires very specific conditions and raises questions about why the jets would be so different from typical cometary jets. The charging timescale for dust grains also matters. How quickly does a particle become electrically charged after being ejected into sunlight and solar wind? If charging happens fast, electromagnetic effects start immediately. If it's slow, particles might travel far from the nucleus before charges accumulate, and forces become significant? The answer depends on grain size, composition, and ambient plasma conditions. For 3I-ATLAS, we don't know these parameters, so we're modelling with broad assumptions that might not apply. There's an interesting feedback mechanism to consider. If dust grains become highly charged, they can affect the local plasma environment through their collective electric fields. A dense cloud of charged dust creates what's called a dusty plasma, where the dust itself is a significant component of the plasma rather than a passive participant. Dusty plasmas have exotic properties. They can support waves, form structures, and behave in ways that pure gas plasmas don't. If 3I-ATLAS's coma is actually a dusty plasma with significant electromagnetic coupling, its morphology could differ fundamentally from typical comets. Bringing this back to observations, the question is whether any of these plasma or electromagnetic effects would be detectable. Certain signatures might be visible in radio wavelengths or ultraviolet, where plasma processes emit differently than neutral gas or dust. If 3I-ATLAS is experiencing unusual plasma interactions, dedicated radio observations might pick up emission or absorption features that optical telescopes miss entirely. Similarly, ultraviolet spectroscopy could reveal ionized species distributions that constrain plasma conditions. The solar wind density and speed at 3I-ATLAS's location can be estimated from models and measurements from spacecraft elsewhere in the solar system, but there's always uncertainty. The wind is variable, responding to activity on the Sun. A faster, denser wind creates stronger electromagnetic effects. A slower, more tenuous wind might make plasma effects negligible. Without in situ measurements at the comet itself, we're extrapolating from sparse data. What makes these plasma theories both appealing and frustrating is that they offer mechanisms to explain the missing tail while remaining within known physics. You don't need to invoke exotic chemistry or artificial objects. Just take seriously the role of electromagnetic forces that are usually minor but might matter for this particular object under these particular conditions. It's conservative speculation, if that phrase makes sense, exploring natural explanations that are less commonly considered rather than jumping to alien hypotheses. But there's a risk of physics shopping, picking mechanisms to fit observations without independent evidence they're actually operating. Ideally, you'd predict plasma effects should produce specific signatures, then look for those signatures. Instead, we're somewhat working backward. We see anomalous behaviour, then asking what physics might explain it. This is scientifically acceptable, but less satisfying than forward prediction. It means multiple plasma-based explanations might fit the data equally well, making it hard to distinguish which, if any, is correct. The hidden forces idea also plays into the broader theme of 3I-ATLAS, operating on the boundary between conventional and exotic. Plasma physics is real, established science, but applying it in unusual ways to cometary environments pushes into territory where models are uncertain and observations are sparse. You're not invoking new physics, just underappreciated aspects of known physics. This is intellectually honest, but highlights how much we still don't understand about cometary behaviour even for solar system objects, let alone interstellar visitors. If electromagnetic forces are genuinely important for 3I-ATLAS, that has implications for how we interpret non-gravitational acceleration. The acceleration isn't necessarily direct evidence of outgassing mass loss rates. Some of the thrust might come from electromagnetic interactions, rather than pure rocket effects from escaping gas. Untangling these contributions requires detailed modelling that we don't yet have. The acceleration might be telling us something more complex than this much gas is escaping per second. One more speculative idea. Could 3I-ATLAS be interacting with the solar magnetic field in a way that generates measurable effects? If the object has any intrinsic magnetic field, unlikely for a comet but not impossible for a body with unusual composition, or if its plasma environment creates induced magnetic fields, those could interact with the interplanetary magnetic field in ways that produce forces or torques. This is getting very speculative, but strange objects demand exploration of strange possibilities. Ultimately, the plasma theories offer partial explanations. They might account for some of the unusual dust behaviour, some of the tail weakness, some of the morphological oddities. But they probably don't explain everything. Plasma effects layered on top, of unusual composition layered on top of unfavourable geometry, might collectively produce what we're seeing. Or maybe plasma effects are minor, and we're giving them too much credit while the real answer lies elsewhere. The appeal of hidden forces and plasma theories is that they keep us in the realm of natural explanations while acknowledging our ignorance. We don't fully understand how cometary dust interacts with solar wind under all conditions. We don't have comprehensive models of electromagnetic effects on small particles in varying plasma environments. 3I-ATLAS might be teaching us about physics we overlooked, rather than revealing something genuinely inexplicable. But teaching moments require learning, and learning requires data we don't quite have yet. Detailed plasma diagnostics, high time resolution observations, multi-wavelength campaigns coordinating optical, infrared, ultraviolet, and radio observations. These are what's needed to test whether plasma theories actually explain 3I-ATLAS, or whether they're just convenient speculation. For now, the hidden forces remain theoretical, invoked but not confirmed, plausible but not proven. As we move toward even bolder speculation in the next section, keep in mind that plasma theories represent the far edge of conventional explanation. If these mechanisms can't fully account for 3I-ATLAS's behaviour, we start running out of natural options. That's when the conversation shifts from what known physics explains this, to what unknown or artificial explanations might we need to consider. The hidden forces are our last defence against the truly exotic hypotheses. Whether they hold or fail determines whether 3I-ATLAS remains a puzzle or becomes a potential paradigm shift. Part 9. Alien Artifact Hypothesis 2.0. Let's address the elephant in the observatory. Every popular article about 3I-ATLAS eventually arrives at this question. Could it be artificial? The hypothesis makes headlines, generates clicks, and causes most scientists to wince visibly. Yet here we are, about to examine it seriously, because while the idea makes astronomers uncomfortable, dismissing it without examination would be unscientific. Extraordinary claims require extraordinary evidence, yes, but they also deserve extraordinary scrutiny rather than reflexive dismissal. Avi Loeb has become astronomy's most controversial figure by insisting that artificial explanations for anomalous interstellar objects deserve consideration alongside natural ones. His commentary on 3I-ATLAS focuses on the missing tail combined with observed acceleration. Loeb argues that if the object is accelerating without proportional visible mass loss, the simplest explanation might be that the acceleration isn't from outgassing at all, but from something engineered. Vents, thrusters, or propulsion systems that don't produce the debris clouds natural sublimation creates. The logic goes like this. Natural comet outgassing is messy. You can't expel gas without dragging along dust. The ratio varies, but it's never zero. If 3I-ATLAS shows acceleration consistent with significant mass loss, but lacks the expected tail, maybe the acceleration mechanism isn't natural sublimation. Maybe it's controlled, directed, purposeful. A spacecraft venting propellant or using solar radiation for propulsion wouldn't necessarily produce a dust tail. The thrust would be there, the trajectory deviation measurable, but the visual signature completely different. This is where the light sail hypothesis enters. A light sail is a thin, large, reflective surface that uses photon pressure from sunlight for propulsion. The concept is real. Space agencies have tested light sail technology in Earth orbit. Japan's Icaros spacecraft successfully demonstrated solar sailing in 2010. The physics works. Photons carry momentum, and a lightweight reflective surface can be accelerated by sunlight without any fuel. For interstellar travel, light sails have been proposed as one of few viable methods to reach significant fractions of light speed given enough time and distance. If 3I-ATLAS were a light sail, either active or derelict, its acceleration would follow naturally from solar radiation pressure, without requiring outgassing. The green glow becomes trickier to explain. Why would an artificial sail emit C2? Perhaps it's covered in organic material accumulated during interstellar travel, frozen volatiles deposited over millennia. Or maybe the sail was intentionally coated with materials to make it appear comet-like, camouflaging its artificial nature. This requires attributing intent and deception to hypothetical aliens, which is pure speculation layered on speculation, but it's internally consistent. Critics point out correctly that there's no direct evidence for artificial structure. No images show geometric patterns, no spectroscopy reveals manufactured materials, no radio emissions indicate power systems. The case for artificiality rests entirely on negative evidence, the lack of expected tail. This is philosophically weak. Absence of evidence isn't evidence of absence, and building extraordinary claims on what we don't see rather than what we do is scientifically problematic. You could invoke artificial explanations for any anomaly if all you need is something that doesn't quite fit expectations. But Loeb's counterargument is that science makes progress by exploring all hypotheses without prejudice. The assumption that interstellar objects must be natural is just that, an assumption. We have no experience with artificial interstellar objects to know what they'd look like. If advanced civilizations exist and have been exploring the galaxy for millions of years, their technology might be common in interstellar space. Dismissing artificial explanations because we haven't confirmed them yet creates circular reasoning. We don't look for artifacts because we assume they're not there, so we don't find them, reinforcing the assumption they're not there. There's a cultural and psychological backdrop amplifying this discussion. We live in an era of heightened UFO interest, government disclosure of unidentified aerial phenomena, and renewed public fascination with extraterrestrial life. 3I-ATLAS arrives in this context, where any anomaly gets filtered through, could it be aliens, narratives. This creates pressure on scientists. Acknowledge the possibility and get accused of chasing headlines, dismiss it entirely and get accused of close-mindedness. The professional middle ground is uncomfortable. The Galileo project, which Loeb helped found after the Oumuamua controversy, represents an attempt to systematize the search for extraterrestrial artifacts using rigorous scientific methods. The project aims to develop sensors and algorithms specifically tuned to detect anomalous objects that might be technological rather than natural. 3I-ATLAS would fit their target profile: interstellar origin, unusual behavior, properties not easily explained by conventional models. But having a profile match doesn't constitute evidence of artificiality, just justification for closer scrutiny. Some researchers have suggested that new AI-driven image analysis might reveal structures in existing data that human observers missed. Algorithms trained to detect geometric patterns or reflectivity anomalies could theoretically identify surface features indicative of manufacture. The claim is that enhanced processing of the November 5th image and other observations might show non-random features. However, these claims remain unverified and highly speculative. Pareidolia, seeing patterns where none exist, is a well-known cognitive bias that affects humans and can also affect poorly tuned AI systems. Without peer-reviewed confirmation, such claims are interesting but not convincing. Let's game out what artificial origin would actually mean. If 3I-ATLAS is a probe or artifact from an extraterrestrial civilization, several implications follow. First, interstellar travel and possibly colonization have been achieved by at least one species, suggesting technological civilization is both possible and expansive. Second, the object might have been in transit for enormous time periods, potentially millions of years given interstellar distances, implying either extreme engineering longevity or the probe was abandoned, derelict. Third, its arrival in our solar system could be random or targeted. Distinguishing these scenarios would require detecting maneuvers or trajectory changes that seem purposeful. For SETI, the search for extraterrestrial intelligence, which has focused overwhelmingly on radio signals, finding a physical artifact would be paradigm-shifting. It would confirm intelligence exists elsewhere and has physical presence beyond its home system. It would shift SETI's focus from listening to looking, from passive detection to active investigation of objects. It would raise questions about whether other asteroids or comets in our solar system might actually be artifacts we've misclassified. The implications cascade outward, touching every aspect of how we think about our place in the cosmos. For astrobiology, artificial interstellar objects would provide proof that technological civilizations can arise and persist long enough to send probes between stars. This constrains the Drake equation variables about lifespan of civilizations and their interest in exploration. It would suggest we're not alone, and that intelligence, once emerged, tends toward expansion. The Fermi paradox, why haven't we detected aliens if they exist, would be partially answered. Maybe they have visited, and we're only now developing the tools to recognize it. But all of this assumes evidence that doesn't currently exist. We have an anomalous comet, not confirmed artifact. The statistical challenge is significant. How many natural objects need to show unusual properties before we're justified in suspecting one might be artificial? If 3I-ATLAS is the first of 100 similar interstellar visitors, all showing comparable anomalies, the natural explanation becomes stronger, apparently interstellar objects are just different from solar system ones. If it remains uniquely weird among an otherwise normal population, the artificial hypothesis gains slightly more weight, though still not conclusively. Occam's razor, the principle that simpler explanations are generally preferable, cuts both ways here. On one hand, invoking aliens is adding massive complexity, entire civilizations, technologies, and motivations we know nothing about. On the other hand, stacking natural explanations to account for 3I-ATLAS might also be adding complexity. Unusual composition plus exotic outgassing, plus geometric hiding, plus electromagnetic effects. At some point you're maintaining the natural hypothesis by making it increasingly elaborate. Whether artificial or exotic natural explanations are simpler becomes philosophically murky. There's also the question of what would definitively prove artificiality. A radio signal emanating from the object would do it. Geometric surface structures visible in high-resolution images. Spectroscopic detection of manufactured materials like pure metals or synthetic compounds. Trajectory changes inconsistent with any natural force. None of these have been observed for 3I-ATLAS. Until they are, the artificial hypothesis remains speculative, interesting to discuss but not scientifically established. The media amplification effect can't be ignored. When a respected scientist like Loeb suggests alien origins, it generates enormous coverage. News outlets love the story because it's compelling and drives engagement. This creates feedback loops where public interest influences which objects get more telescope time and funding, potentially at the expense of less sensational but scientifically valuable targets. Scientists worry about this distortion of research priorities and the damage to astronomy's public image if every anomaly gets sold as potential aliens. Yet there's value in the discussion, even if the conclusion is ultimately natural origin. By seriously examining the artificial hypothesis, we clarify what evidence would be necessary to confirm it. We develop methodologies for distinguishing natural from artificial objects. We prepare conceptual frameworks for the possibility, however remote, that someday we might encounter actual extraterrestrial technology. The intellectual exercise has merit even if 3I-ATLAS isn't the case that confirms it. What frustrates many scientists is that the alien hypothesis is unfalsifiable in a practical sense. You can always say we haven't looked closely enough, haven't used the right instruments, haven't thought creatively enough about how alien technology might appear. Natural explanations can be tested and potentially ruled out by observations. Artificial explanations can perpetually retreat into "we don't know how aliens would build things" territory. This asymmetry makes the debate feel unproductive. However, if we're honest, the same unfalsifiability applies to some natural explanations. You can always propose more exotic compositions, more unusual environmental histories, more complex outgassing mechanisms to fit any observation. Natural explanations can also retreat into increased complexity, rather than being definitively ruled out. Perhaps the real issue isn't artificiality versus natural, but how we handle ambiguous cases that resist clean explanation regardless of origin. The alien artifact hypothesis represents humanity's cosmic optimism and paranoia simultaneously. Optimism that we might discover we're not alone, that intelligence is common enough to have sent probes our way. Paranoia that we might be under observation, that something out there is watching us, that the universe is less empty than we'd assumed. 3I-ATLAS becomes a Rorschach test. We see in it what our assumptions and hopes lead us to see. Whether 3I-ATLAS is artificial won't be settled by speculation. It requires data, observations that either confirm natural mechanisms or reveal evidence inconsistent with them. The object is still visible, still being tracked, still yielding information. As months pass, we'll learn more about its composition, behaviour, and morphology. That data will either narrow the possibilities toward natural explanations or keep anomalies alive that justify continued consideration of alternatives. For now, the alien artifact hypothesis remains what it has been since Oumuamua, a tantalizing possibility that can't be confirmed but also can't be completely dismissed given current evidence. It serves as a boundary marker for the discussion, the extreme end of the possibility space. Most scientists believe we'll eventually explain 3I-ATLAS naturally, that its weirdness reflects our ignorance rather than genuine artificiality. A small but vocal minority argues we should keep an open mind, follow evidence wherever it leads, and not let cultural biases against extraterrestrial intelligence blind us to possibilities. What we can say with confidence is that whether 3I-ATLAS is natural or artificial, it's teaching us something. If natural, it's revealing diversity in interstellar objects and potentially new physics of cometary behaviour. If artificial, it's announcing we're not alone. Either outcome is scientifically profound. The uncertainty itself is valuable, forcing us to question assumptions and refine methods. Sometimes the journey toward an answer teaches more than the answer itself. The alien artifact hypothesis 2.0, applied to 3I-ATLAS, is more sophisticated than simple UFO speculation. It's grounded in specific observational anomalies, proposed by credentialed scientists and discussed in peer-reviewed contexts. It deserves neither reflexive acceptance nor dismissive rejection, but careful, evidence-based evaluation. That evaluation is ongoing. The cosmos will eventually tell us what 3I-ATLAS is. Our job is to listen carefully, observe thoroughly, and remain humble about how much we don't yet know.